All right, in this video, we're going to talk about p-series, which is another test for us to establish whether or not an infinite series converges or diverges. And so in the last video, we talked about the integral test, and of course, the sequence must be able to be transferred into a function that could then be integrated, and so that's one of the leading ideas behind choosing the correct test. The p-series is another one where you kind of have to be given the information in an appropriate form or be able to manipulate it to get it there. For p-series, you're going to have this 1 over n raised to the p. And if that's the case, if p is bigger than 1, the infinite series is going to converge. If p is less than or equal to 1, then the infinite series is going to diverge. Okay, now one of the most important examples you could read in this chapter is going to be example 3 on page 588. It's going to walk you through this, and this is a very similar exercise to one that you worked earlier in the course, in particular when you worked with improper integrals. As you work through this, you'll be able to recognize now where the harmonic series comes into play and how the harmonic series in fact does diverge. So take a little bit of time and really read through that example. It's going to be a really good one for understanding this particular test. So the problem that we're going to look at dealing with it is going to be the infinite series from n equals 1 to infinity of 1 over the cube root of n plus 3 raised to the 4th power. Now, as you look at that, you might be thinking to yourself, well, how in the world is that going to come into this form? Well, there's going to be a pretty interesting way of handling this, one that we probably haven't done, but we did talk about. And so you're right, this is not in a form where you can proceed by testing convergence or divergence using p-series. But if we manipulate this, along with where we start, we might be able to hit our mark. So follow me on this. If I re-index, if I change my index, let's say to 4, and I take this exponent in my numerator, it's going to leave me at a 1. And then in my denominator, by re-indexing at 4, I need to get the same number first as I would if I used 1. Well, that means I'm just going to have an n to the 1/3 on bottom. But if I now combine that with the outside exponent, that's going to give me a 4/3. Now, I know that's a bit of a stretch if you're not as experienced with infinite series or working with series as others, but that's okay because you can always check it. Remember, if n is 1 and you put a 1 right there, that's going to give you the cube root of 4 then to the 4th. Well, if n is equal to 4, notice how it gives you the same thing. And this was one of the properties in that theorem I discussed a few videos ago. I think there were 4 different parts to it. We can delete a finite number of terms and it doesn't affect convergence or divergence. In this particular case, we just re-indexed. We didn't even delete terms. We just re-indexed to make this look a little different. Now that we're in the appropriate form, since our p is going to be equal to 4/3, which is bigger than 1, we can say, therefore, the original, much more complicated looking series would converge by p-series. Converge by p-series because of that p being bigger than 1. We know that now it's going to converge by p-series. So this is a nice test if you can make it work. Now, it won't always be available to you depending on the series, but if you can manipulate, re-index, the chances of it working and being a very simple solution are definitely in the cards.